All right, hello everyone. So here we're going to do a couple of videos on integrated rate laws. So in our last set of videos, we talked about how we use the initial rates. So if we focus on the initial rate of the reaction, we said that we can simply take the slope of that linear portion of the graph, and then of course we use the initial rates to come up with the rate laws, and then also use the rate laws to describe the mechanism or how the reactants are interacting with one another. Now though, we want to focus on what's happening to the rate over the entire course of the reaction. So if we look at the graph now over the entire time frame, we can see then that we have this rate that changes over time. So at the beginning of the unit, we talked about how at the beginning of the reaction, we have a faster rate because we have a steeper slope, but then at the end of the reaction, we have a slower rate because now the slope has become more shallow, it's less steep. So the question is, how can we then come up with an equation or a function to deal with this changing rate? And so hopefully remember that we can use calculus to then describe a variable that is changing over time. All right, and so we can account then for the fact that this rate is slowing down over time. So what we want to do is we'll first look at an example where we have a first order reactant. So let's start writing out what we might be dealing with. So let's say we have just a simple reaction where reactant A decomposes to two new components. So we'll just have some basic decomposition reaction. So we know that we could come up with a rate expression. So the rate of this reaction would equal minus the change in concentration of A over the change in time. So this is just from our basic rate expressions that we talked about earlier in the unit. And we could also write a rate law where we now know that the rate would equal a rate constant times the concentration of A. And we'll assume that this is a first order decomposition, so the reaction order would equal 1. Okay. Now, since we're describing one reaction, we know that these two rates ought to be equal to one another because they're describing the same reaction. So let's now set these two terms equal to one another. Okay, and now we can basically set up a differential equation. So we can express this equality as a differential equation. So now we can say minus dA dt equals K times A. And now we'll rearrange this differential. And then we can integrate from time 0 to some time t. Which is just going to be some time in the reaction. Generally be pretty far along in a reaction to where we've gotten the slope leveling off, as we saw in our previous slide. All right, so it turns out that if we do that, so we can say that at time 0, the concentration of our reactant at time 0 will integrate to the concentration of our reactant at time t. We pull the negative out, and so then we just have this integral. And we can pull out the constant and integrate from time 0 to time t, dt. And then we can then simply use the standard integral, and we would solve and find that this left side of the equation would give us a natural log of AT minus natural log of A0. And of course, that would equal K times T. And we can now rearrange the result of that integral. So we know that if we subtract 2 natural logs, we then divide. Move the minus sign over to the other side. All right, so this is essentially then the function we can use to describe the fact that this reaction is changing rate, that it's slowing down over time. Now we can actually rearrange this so that we can get it into a linear form. And hopefully you now recognize that this has the form y, oops, equals mx plus b. So if we plot the concentration of our reactant at any time t versus time, right? So we're going to plot concentration versus time. Well, to be more specific, we're going to plot natural log of concentration versus time. We should then get a linear plot. So it should look something like this. So if we have natural log of A versus time, we of course would then see a plot that looks something like this. Should be linear. Okay, so now we have a way to plot a linear graph that's going to show us then the changing rate over time, and it's due to this derivation that we just did here using this integration. So this is why we call these integrated rate laws or time integrated rate laws. So if the reaction order is 1, if it is indeed a reaction order of 1, then if we plot natural log of A versus time, it should be linear. Now notice that the slope of this graph should give us the rate constant. Now also notice that we have to take the negative of the slope, right? Because we see the negative sign in our expression, but we can see that with this plot, the slope would be negative, and we want to have a positive rate constant. So if we take the negative of a negative slope, that gives us a positive k, which is of course what we want. We want to be able to express the rate constant as a positive. All right, so we have a way to now mathematically address or describe this changing rate, and we even now have a way that if we can measure the concentration over the entire time frame of the reaction to the point where the reaction starts to stop, we can then get K from that. All right, so that's just an example of how we could could derive this linear equation using this fairly basic calculus. Now, don't panic. I'm not going to expect you to do the calculus to go through this derivation, but just want you to appreciate that calculus is required to come up with this linear expression, which then of course gives us this type of linear plot. All right, so here's just a nicer graph. So again, if we plot the decomposition of A, we should get a decrease in concentration over time, as we talked about at the beginning of the unit. And of course, as time goes on, the slope decreases, and so we get a slowing of the reaction. So if we use our first order time integrated rate law and plot natural log of A versus time, now we get that nice linear plot based on this function that we came up with on the previous slide. And of course, we can say that the slope equals negative k. So if we take the negative of the slope, that gives us the rate constant. All right, so we could then use a similar derivation to do the second order rate law. So here we can see that now if we have A again decomposing, we would say now the rate equals, well, I'll write it over here. The rate would again equal minus change in concentration in A over change in time. If it's a second order reaction, now we would say that rate equals rate constant times concentration of A squared. And again, we know that these rates would be equal to one another because it's describing the same reaction. And so now we say that the rate expression would equal the rate law. But now the change is that instead of having a first order reaction, we have a second order reaction. So if we go through the same type of derivation, so if we set up the differential equation, take the integral from time 0 to time t, solve for the standard integral, then we would get this form. So instead of natural log, it turns out then that we would get 1 over concentration equals kt plus 1 over concentration at time 0. So now again we have a y equals mx plus b type of equation. And so now we can plot 1 over concentration versus time. And if we do that, we get a plot that looks like this. And of course, again, k is our slope. Now notice this time, because it's a positive slope, we don't have to take the negative of it. It just gives us the rate constant outright. Okay, so again, if we look at a slightly nicer version of this, we look at the if we were to take the second order reaction, if we just plotted concentration versus time, we would see a curved graph where the rate changes over time. Of course, it's decreasing because it's a reactant. If we take the natural log, that's the first order, that also gives us a curved graph. So now we know that if we plot natural log and it's not linear, it must not be a first order reaction. So this is not a first order reaction. But then if we take 1 over concentration versus time, that now gives us a linear plot. So we take 1 over concentration versus time. So this tells us it's second order. Okay, so just a quick overview of how we can use some basic calculus to now describe the rate of reaction over the entire time frame of the reaction. And the key reason why we want to do that is, one, it now allows us to solve for the rate constant without doing these initial rate types of experiments. So it's going to be a little bit easier to just track the concentration over time. You don't have to do multiple experiments. And then, as you'll see in a moment, now that we have these functions that can describe the entire reaction, we can begin to predict, well, how long is the reaction going to take overall? So we can start to kind of plan how much time we would need to devote to get a significant amount of product. All right, so we'll stop there. And when we come back, we'll talk a little bit more about how these integrated rate laws allow us to describe the reaction over the entire time frame, and how we can predict how long a reaction will take. And we'll do that by looking at the reaction half-life. All right, so we'll see you in just a moment.